Alrighty, good morning, ladies and gentlemen. Welcome to Yokogawa's Analytical Web Seminar, Practical Considerations of CO Measurement in Coal-Fired Power Plants. We would like to thank you all for taking the time to attend, and we hope you find this seminar helpful and informative. Before we begin, we would like to go over some housekeeping issues. The audio part of the seminar can be accessed either through the teleconference number provided in the Info tab of your WebEx Manager window or through your PC speakers. To hear the audio through your PC, select the Communicate tab and join the audio broadcast. The seminar will last approximately 1 hour. Towards the end of the presentation, where time permitting, we will have a question and answer section where a featured speaker today will answer some of the questions received from the audience. If your question is not answered during the presentation, please be assured we will answer them directly either via email or phone. All questions should be submitted in either the question and answer window or the chat window located in the lower right-hand corner of your screen. Our featured speaker today is Jesse Underwood. Jesse served a 5-year United Association apprenticeship where he learned industrial drafting, instrumentation, and process control prior to becoming a technician for DuPont. He later became an area sales rep for Analytical Specialties, which was acquired by Yokogawa last year. Today, he provides sales and technical support for both analyzer function as well as application specialist for the new Yokogawa Laser Analysis Division. We would like to get the seminar started by handing it over to our featured speaker, Jesse Underwood.
Thank you very much, Sherilyn. I'd like to also thank all for choosing to attend today's webinar, especially those who are working after hours overseas. I saw a few on the attendee list. I would like to shed a little light on a subject that has been a challenge for the coal-fired power industry since its inception, which is measuring the constraint of carbon monoxide, or CO. There have been many attempts with many technologies, but we are confident that it can be accomplished with our TruePeak tunable diode laser analyzer in the location that best represents the real CO value. Combustion has not changed much over the years. A balance of fuel, air, and heat is the goal. But finding that balance, however, is a challenge. There are many considerations and variables, but these four sum them all up. Safety is the most important, and that is protecting your equipment, your people, and your assets, and these must be included in any conversation which would modify your system. As for efficiency, the principal goal is to increase the amount of heat that is generated out of a specific amount of fuel. This is usually approached by reducing the volume of excess air, thus, email's coming in, pardon that, stop that. For efficiency, again, we're trying to increase the heat capacity or increase the amount of heat that is generated out of a small amount of fuel or specific amount of fuel. And that is approached by reducing the volume of excess air, thus allowing the generated heat to do the job in which it was intended to do, and that is to make steam. A very large part of the operational cost of one of these facilities is fuel, and the power industry has done a great deal of work to improve this. And throughput ties very closely to this efficiency and the fact that when the excess air is removed, your optimal operating temperature can be more easily achieved. Also, we have found that if the excess air is removed, then you have removed a mass of nitrogen and oxygen, which contributes to the pollutant NOx. Also, if you are using less fuel to create the same temperature, which is carbon, then less CO2 is being generated as well. All of these tie together because as the excess air is reduced, the risk of running fuel-rich is present. This is where having the diagnostic of a real-time CO measurement in the right location can significantly contribute to all four of these goals. In the past, the primary means of understanding what is taking place in the combustion process has been measuring oxygen, and there are several reasons for that. First of all, it has been the easiest to measure. The zirconium oxide technology has a very long track record and has been proven reliable and is obviously well documented. The average oxygen content of the flue gas typically changes in a very gradual manner when the conditions are changing, and those conditions can be quite vast. CO, on the other hand, has been very challenging to measure for the industry, despite many efforts of many kinds. Even when you are able to measure it effectively, the dramatic changes of concentrations can make it difficult to control off of. So we are not advocating control with CO, but rather using CO breakthrough as an indication of the optimal excess O2 level. And on the chart here, it's a fairly typical graph showing the relationship between oxygen and CO, where on one side you're fuel-rich and one side you're air-rich, and the goal, of course, is to meet somewhere in the middle. But where is that optimal O2 set point? Some people have said that on their system it's 2% or 1% excess oxygen. Some plants run at a much higher level. But we believe to gauge that, you must have some type of indication other than just oxygen, because there are many factors to consider. So we think that it is the lowest oxygen set point possible without generating carbon monoxide. And all of this can change continuously in your side of your boiler with different BTU values of your fuel, the different burner wear. They're not all burning the same. Several factors can contribute, and that is why we believe the diagnostic of a CO measurement can absolutely determine where that O2 set point should be. This is a graph that was taken at a refinery, and the context is not to show you the difference between a gas-fired and a coal-fired, but just to show you the concept of the reduction of oxygen and the production of carbon monoxide. On a gas-fired system, safety is a much more important because the raw fuel can be explosive downstream. So in many cases, when they do not have a diagnostic of carbon monoxide or any type of fuel downstream, they run on the safe side, which is a air-rich side. So before these analyzers, these tunable diode lasers were installed on their process, they ran at an average of 4.5% oxygen. But after they installed these TDLs, one measuring carbon monoxide and methane and one measuring oxygen, they had an operator test where they drove the oxygen value down. And we can see very clearly at this 1.5% oxygen mark, a mass of carbon monoxide was generated. And then as the operator increased the oxygen back up to 1.5%, the CO value came down. And this is just a crude example of the relationship between air and fuel and the balance that we're trying to find. So this is basically a summary of what we've talked about so far. The ability to detect carbon monoxide crosses a number of key factors in the combustion process. So not only does it allow you to reduce the amount of excess air, which increases heat capacity, but also gives you an early indication of a fuel-rich environment. There are some considerations that have to be taken when choosing a technology. Placement at a crossover or radiant section, nose arch, radiant, superheater, before the CO has a chance to afterburn or react with oxygen and convert to CO2. Also, coverage across the burners to measure breakthrough at any one point. We call it a path average that the laser is performing. sensitivity to allow parts per million measurement, which would result in a safe O2 level, speed of response to allow reaction to changing conditions, and low to no interference from other combustion gases such as CO2, moisture, or any type of combustible. So why isn't everyone in the industry making this measurement? Well, most of the technologies that have been available were not designed specifically with pulverized coal business in mind. One of the original technologies for measuring combustion gases that had early and sustained success was catalytic bead sensors. A later revision to the technology was using a solid-state metal oxide semiconductor. This eliminated the consumption of the catalyst and extended the life of the sensor. Even with this advancement, the sensor must come in contact with the target gas to generate a signal. Another analytical technique that was implemented for measuring combustion gases was the NDIR, or non-dispersive infrared filter photometer. The design of this system is much more conducive to the harsh nature of the coal power industry. The main reason for that is the sensor never comes in contact with the process. This greatly extends the life of the sensor, and it works on the principle of infrared vibrational absorption spectroscopy. The solid-state sensor technique, because of the harsh environment, has to have some type of extraction system, meaning that you have to take a sample out of the boiler, put it through some type of filtration system to clean it up, and then pass the flue gas over the sensor. So because we have a filter involved, this filter has to be cleaned, and you could imagine with the mass of fly ash that's going by, that filter would need to be cleaned very often. So while this system can work, it does require a lot of maintenance. So this also only gives you a single point of measurement, whereas a boiler can have a very large volume. You're just pulling out a single point of the boiler to try to represent what the overall value is of the carbon monoxide. The NDIR technique, while having superior advantages, has some limitations. One of those limitations is temperature. And this type of technique can only be applied downstream of where the actual combustion is happening. And when you take a measurement of carbon monoxide far from the fire, you're getting a false low value because the CO is reacting into carbon dioxide. So with the traditional or early techniques of measuring carbon monoxide, there were also some accuracy considerations. With the solid-state sensors, the catalytic bead or the thick-thin film sensor, the accuracies list 2 to 5% of reading. But that's not necessarily what the actual reading might be. The NIST, there's several other affiliations that have performed their own tests, and these accuracies have been a little bit more loose than the stated accuracies from the manufacturers. The thick-thin film sensors also have a little bit of interference from SO2, NO2, and water, which can be inherent in combustion gases. Also the NDIR definitely has interference from water, which in any combustion is the goal, is to have CO2 and water, which are the radiant gases. So this is another crude drawing of a coal-fired powerhouse, showing you some of the places where these traditional technologies have been applied or tried to be applied. Realizing that the closer to the fire you are, the more representative the CO measurement is. I've talked to several people who have tried to apply these point sensors, whether it's catalytic bead or thick-thin film, directly over the fire to get that representative measurement. But as you can imagine, you have this fly ash in a plasma-like state, and trying to pass that through any type of filter system can be incredibly problematic. And then to deal with the temperature limitations of the standard infrared type analyzers, it had to be downstream of where the CO is being quenched. So these are the considerations for the traditional technologies. So I'm going to go into great detail about the TDL technology, but it too is an optical device, and the sensor does not touch the process. However, this laser technique does not have the same temperature limitation, so we can utilize this technique anywhere in the process, whether it's hot or cold. So, to give you the optimal CO value, we can put it directly in the radiant section, superheater, etc., to give you that most realistic CO value. So some of the simple advantages of a tunable diode laser system is that we can give you that measurement in the firebox, which gives you the most representative measurement. Also, it is an in situ or across the firebox measurement. So we have no sample system which could potentially fail or need maintenance. Also, this reduces the lag time. Most TDL systems have a response time of less than 5 seconds, and this is a full step change, whereas most analytical techniques have a time response factor, and this can be 30 seconds, a minute, 2 minutes. Also, this optical technique, whether it's NDIR or TDLS, gives you a path average measurement. And this simply means that we're counting up all of the carbon monoxide molecules in between the source and the detector, and then averaging that over the entire span. So we're giving you basically an infinite amount of number of points all in one measurement. So with the zirconium oxide technology, this is sort of typical to what you would see in the backpass. You would see multiple analyzers, and the reason for this is to try to obtain some idea of what the average across the combustion section is. So you can see that to make sure you have a balanced load on your burners. With one tunable diode laser analyzer, you get the entire path average with just one instrument. And the reason that this is important is because stratification is inherent with any combustion system. This graph you see here was made with a portable oxygen analyzer, and we just held a probe out at different lengths over a area of the radiant section and found that there were a dramatic difference in the oxygen concentration values. Now, these values would directly reflect what the carbon monoxide values were. Where you would have low oxygen, you would have high carbon monoxide. So the analyzer, one specific analyzer, would not tell you what each area is, but rather give you an average of the whole. This chart is a little hard to understand, but I'm going to try to set this up for you as best I possibly can. So what you see up here in the top left-hand side graph, the bottom lines are the CO values, these here. These are the CO values, and we had 2 point sensors, those catalytic bead types, and then we had 1 TDL reading carbon monoxide as well. The gases on the top are oxygen. So this boiler was approximately 60 feet or 20 meters across, and each one of these point sensors was 20 feet from the wall. So it was basically split into thirds. And what we're trying to represent here is that the CO laser, with this one path technique, was able to pick up carbon monoxide when the point sensors were not able to because of their location. So as you see here, the oxygen value was moving along quite steadily, and then we see a dip in the oxygen concentration, and that resulted in a response from one of the catalytic bead sensors, but not both. So one read 267 ppm during the almost zero oxygen event, and one did not read any CO. But the TDL read 8,700 ppm. So the TDL was able to pick up the CO excursion from one particular area of the boiler that was not representative in the point sensors. Okay? And then you see the operators brought the value back up to a safe state, and then we saw another low oxygen event here, and this time neither CO point sensor caught the event while the TDL read 2,000 degrees. And then in the last event, here in the low oxygen event, you had one CO point sensor catch the entire excursion. And we say entire excursion because that value was also the same value as what the TDL read, close to 1,300 ppm, while the other did not catch the event at all. So this graph is specifically designed to help you understand the advantage of a path average over a single point sensor. So some of the simple advantages as an attribute of the type of technology is the accuracy of the TDLS system. So we are using a very coherent light, a monochromatic light, producing a single color, and we can focus that light to whatever size diameter beam that we need for the distance across the boiler. So because we're only producing one color or one wavelength of light, we can be very specific in just measuring the carbon monoxide infrared absorption and not have to worry about CO2, moisture, SO2, other gases that could potentially interfere with other types of technologies. And we've also validated this information in the field. So how the tunable diode laser system works is on the left-hand side here, we're showing you our laser controller, this box here. This has a computer in it and a laser controller. And then we have a laser that's inside of this barrel that's mounted directly in line with a detector on the other side. So whenever we turn the laser on and tune across the peak of interest, this is why we call it a tunable diode laser, what we see here is we introduce a small amount of current change over a given or constant period of time. And this happens at a rate of 1 kilohertz, or 1,000 times a second. So what the laser driver is showing is this current ramp here in this box. What the detector sees on the other side, if there's any CO gas present, or oxygen if that's our target, would be here. You would see a loss of light over the current ramp. We take that signal that's produced from the detector and we amplify that milliamp signal into volts in this box here, and then transmit that back over to the controller for interpretation. So we take 1,000 measurements a second over about 5 seconds, which we can do more or less if the customer would want. And what the analyzer would interpret is this beautiful peak here, absorption peak. And then we, in turn, interpret that into gas concentration. So it's a relationship between the amount of light that made it across and the light that is actually absorbed. And the delta helps us to interpret the gas concentration. So we seriously advocate the type of analysis we make by putting the laser directly in line with the detector. There are other tunable diode laser companies that transmit the light from a remote controller via fiber optics up to the process. Now, we have done a thorough investigation and due diligence on our part to try to find the advantages of this type of system. But we believe that having the laser and detector directly in line with no components in between greatly increases the uptime and reduces the failure rates of the system. Now, one great advantage of the type of technique we use with having the laser and detector directly in line is that we can use a wavelength of light that allows us to have a very high sensitivity to carbon monoxide. To our understanding, these fiber optics have a bandwidth of light that they can transmit through them. And that bandwidth of light does not include the wavelength of light that we're using for this high sensitivity CO measurement. So our typical accuracy for a coal-fired boiler in the radiant section is about 5 ppm. Also with our system, because we're able to directly control the diameter of beam that's produced whenever a customer tells us the size of their boiler, we can program in or dial in that diameter beam as large as we need to make sure that the alignment stability stays good. So with our alignment technique, whenever we dial in the size of the beam, we can lock in those alignment and feel 100% confident that we will not lose the light transmission due to alignment. Also, by using this direct laser technique, we also deliver the maximum amount of power the laser can produce directly through the process. So with this type of system, this tunable diode laser system, it is an entire solid-state component. So the field maintenance is very low. There's no moving parts, and there's nothing changing states, which in turn gives a great uptime on the equipment. So this is an illustration of our large aperture optics, as I was describing as dialing in the beam diameter of the analyzer. So again, the laser itself is in a small chamber here mounted directly to the controller. And we pass that laser light through a diverging lens, and we can set that lens to control the diameter of the beam. So we have done this, accomplished this on coal-fired powerhouses at a span of up to 67 feet, but we also were still getting a large amount of the light transmission. So we're very confident that we could do greater spans. We just haven't had the opportunity yet. So some customers say that they want to diagnose the different areas inside of their boiler where the CO is being produced. So this TruePeak system is a one measurement per one controller system. So you have true redundancy. If you have two measurements, it's two controllers that operate independently of each other. So this system is scalable on how many points of measurement that the customer may want. So there is no limitation of how many can be used, and these are all operating strictly independent of each other. So if one fails, the other one will keep working. So we have had a field trial in Wyoming, United States, 650 megawatt pulverized coal-fired boiler. This was in the superheater section with a temperature that ranged, depending on the load, between 21 and 2,600 degrees Fahrenheit. So our group, the Laser Analysis Division, has been through a complete Department of Energy program called Advanced Diagnostics and Control of Furnaces, Fired Heaters, and Boilers. But this was specifically for the petrochemical industry. And some of the challenges were similar to what we found in the coal-fired industry. Things like radiant light in the background, thermal expansion of the boilers. But going into the coal, we had no idea just how extreme all of these variables would be and how much more greatly different they would be than in the gas-fired world. So with our experience with the background light, we found that it was almost one order of magnitude greater, that is the frequency changes of light in the background than it was in the gas-fired field. So we had to make some changes to our radiation filter on our detector, but we were able to meet that challenge. Also, because of soot blowing, we saw a vast dynamic of the dust density inside of the boiler. However, we were able to make changes again to our detector, the way we amplify the signal, to deal with the difference between normal operation and when you have local soot blowing. So we were able to validate the carbon monoxide readings from our analyzer with the user's SEMS information. However, the customer did not have a local temperature measurement where the analyzer was. So, understanding that the temperature was in a certain range of 21 to 2,600 degrees, we plugged in the median value of 2350. And this is very important because temperature has a bearing on gas density. So our analyzer is just counting how many CO molecules there are and dividing it by the distance. However, if the density is changing, we normally input the temperature value so the analyzer can compensate for that. But in the coal-fired world, temperature is not always easily obtained. So in that median value of 2350, this just means that the accuracy would be plus or minus 10% of reading instead of plus or minus 2% of reading, which is what we normally specify. So here's a graph of the online outputs that the analyzer was giving, that is carbon monoxide in the ppm range, and light transmission. So the light transmission is shown with this pink line here on the line graph, and you can see that our transmission value is consistently over 20% and usually up 50 to 70%. And again, this was obtained by using some techniques in amplification of the detect signal. So being that this measurement was very close to the fireball, you can see that there still was a mass amount of CO in that section. It wasn't down like you see in the gas-fired where it's normally 0 to 50 or 0 to 75 ppm, but rather it was much higher. So the type of boiler that we did our first test on was a tangential fired boiler. And from our understanding, a tangential and a wall fired have a similar profile as far as the amount of fly ash it produces. So we feel that 100% we are ready to tackle any wall fired or tangential fired boilers. We will be installing 2 analyzers probably within the next month on cyclone-fired boilers that we will be evaluating separately. We want to be 100% sure that when we sell something it will work, so we want to put in our due diligence to do these evaluations. So the critical parameters of consideration for a tunable diode laser system would be the optical path length, which we would obtain with your firebox dimensions. The temperature range, because that will have an effect on the fly ash density. And then what your expected and desired CO ranges and targets are. So if there is any interest, we can send an application data sheet where you can give us these key variables, and then we can do our application engineers can go through all these parameters and give you a predicted transmission strength and predicted CO accuracy. So in the next 2 months, we will be installing a TDL analyzer with an oxygen laser to perform a full field trial test. So with our system, there's very small changes to hardware on what wavelength we want to emit to what gas we want to measure. So all of the field trial time and successful runtime on sold units that we have absolutely can go toward our oxygen analyzer, because it's just a single component. It's the laser diode that changes from CO to oxygen. So we're very confident with that. I absolutely appreciate everybody's time, and I would love to take some questions.
Thank you, Jesse. We do have a couple questions. First question is, what is the maximum distance between each TDLS?
That is a great question. And it's not a set value because conditions in each boiler can be different. I said during the presentation that we have done up to 67 feet, but we were still getting 50% of the light transmission. So I would feel absolutely confident that we could do up to 90 feet or maybe even 100. But again, the key variables would be what is the temperature, and then what is the dust density, what is the mass per volume, and that can be a tricky number to obtain. But if we know the mass per volume, and then we know the volume and temperature, our spectroscopist can give us an expected transmission value, whether it's 1% of light transmission or 20% of light transmission. They can accurately predict that.
Okay, and we got a couple more. Can some TDLS or TDL devices measure both CO and oxygen at the same time?
It's a very good question. So, if the question was TDL devices, well, I guess it would be no in both no if it was a tunable diode laser, because the laser emits a very narrow wavelength. But a device, if you had one controller with both an oxygen laser and a CO laser, I do believe you would have to alternate between lasers in that one device. So while one device could potentially measure both gases, I believe you would have to alternate between which gas you measure at one particular time. Does that answer the question?
I believe it does. If not,
okay.
They can email analytical@us.yokogawa.com if the question wasn't answered thoroughly for you, and we can get you more detailed information.
Sure.
Another one, for what applications are large aperture optics recommended over the standard optics?
That's a very good question. Our rule of thumb is 20 feet or 6 meters, and that's just because our experience with thermal expansion, the characteristics of it. However, it doesn't require 20 feet for us to use those large aperture optics. We can use them at our discrepancy, at our discretion. We can say, due to the extreme heat, thermal expansion or extreme temperature difference between cold start and operation, that we can then use those devices. I see Aaron Hemphill has a question. Do we have any references available?
We answer those. I just sent him a message. We will answer his questions one-on-one.
Okay.
Got a couple.
Certainly.
Thank you guys for taking the time to join us today. We hope that you found the seminar informative and a little helpful. Like I said, if you have any other questions, please feel free to contact our Laser Analysis Division at 281-488-0409, or you can email us with any questions to analytical@us.yokogawa.com, and we will get someone to contact you and be able to answer any of your questions. Jesse, thank you for your time today. And we'd also like to mention that the seminar was recorded and will be able to be replayed 24 to 48 hours after today under the webinar section of our website. And we hope to see you online at our future webinar sessions. Thanks. Have a great day, everybody.